You're watching PowerNation. Today on Engine Power, we're building a winning Windsor. And the best part about it is, well, you'll just have to watch to find out. Hi everyone, and welcome to Engine Power. We are very excited to start a brand new project for you. Now, we've done a few Chevys and even a small block Mopar, but today it is all about Ford power. These are the makings of a 410 cubic inch stroker small block Windsor. Now this is going to be a heavy hitter on pump gas, but what makes all this extra special is we have partnered up with Holley so you can enter to win this exact engine for yourself.
And that's really exciting for one of you because this engine is going to come with a bunch of great parts, including a fully forged rotating assembly with Eagle crank and rods and a Molle piston, a set of AFR 220 competition ported cylinder heads, a Holley high ram intake manifold with their 105mm throttle body intake top, and the whole engine will be controlled with Holley EFI, including their Terminator X Max and their Smart Coil kit. But before we can get all of this in there and get it in one of your driveways, we have a lot of work to do, including some block prep.
A bunch of that.
So let's get started. First up is removing the threaded oil gallery plugs throughout the block. This will allow us to drive out the pressed-in plugs in the front of the engine. We'll do this with a long piece of threaded rod and a hammer. To remove the plug from the lifter gallery crossover port, we'll drill a pilot hole, run in a self-tapping screw, and use a slide hammer to pop it out. Next, we'll port the oil inlet from the pump using the gasket as a template. A series of carbide burrs and a light touch gets the job done safely. It's important to go slowly and check your work. We say it often, but it bears repeating. It's easier to remove more material, but very hard to put it back. Throughout the process, we'll continue to use the gasket as a guide. To further smooth out the finish, a cartridge roll comes next. Once we're happy with the surface, we'll follow the oil's path, smoothing as we go. It's important to have a wide variety of carbide shapes and sizes to get into all the block's nooks and crannies.
Moving on, we'll tune up the drain backs in the lifter valley. Notice that the burr is running at moderate speed. This helps maintain control and not move too fast. We'll give the same treatment to the pressurized oil crossover for the lifters. We are tapping the oil galleries that had press-in plugs in favor of threaded pipe plugs. This serves a couple of different purposes. First, the plug cannot pop out under pressure, unlike a pressed-in one. Second, it makes the oil galleries easily serviceable since we can readily remove and reuse the plug. The holes are tapped so the plug is just under flush from the surface, because if you go too deep, you can potentially block off another oil gallery. Once we're happy with the fit, we'll chamfer the outside. Every bolt hole is finished with a light chamfer.
There are several reasons to deburr a block, which we'll get to in a minute, but the one that is my favorite is that it stops the paper shop towels from tearing when you're wiping off the engine.
Oh yeah, very nice hustle on this one.
Yeah, I mean, it wasn't too bad. A couple hours into it, but the great part is that this block is definitely going to benefit from this. So.
I would agree with that. Now, this seems like a tedious task, but this can benefit any engine that you work on. I don't care what it is. Smooth oil flow is always a great thing, and working with a block that you can't cut yourself, and deburring it eliminates places for stress risers to start. So whoever gets this one is going to get a nice piece. What's next?
We got to clean it. I mean, I'm pretty much done here. It's all deburred. The oil returns are all smoothed out. All the pressure ports are all smoothed out. So got to get this in the cleaner, get the bores cleaned, get all the oil galleries cleaned, and then we can move on to assembly.
To the cleaner.
All right.
Bring it with you.
It's oil galleries, not galley. A galley's a kitchen on a ship.
Yeah. Our jet washer runs at 150 degrees, so we'll use it to wash the block for about 30 to 40 minutes.
Up next, they may be small, but piston rings can have a big impact on your engine's performance.
With Frankie's enthusiastic and strangely cheerful help, assembly of the 410-inch Windsor begins. To ensure that the cap is aligned and the bolts won't bind up in the bolt holes, we start by gently running down the fasteners, and then we tap the main with a dead blow hammer to seat it. Now the bolts can be snugged down and torqued to a final value of 100 pound-feet. The crankshaft journal is precisely measured with a micrometer, and that measurement is transferred to our Sunnen dial bore gauge. With the bearings installed, the housing bore is measured to determine its vertical oil clearance. Number 5 main measures right at 3 thousandths, which is technically 1/10,000th above the stock spec, but for our high-performance engine, it will work great. As always, we do this for every housing bore. The same process is done for each individual connecting rod. We'll measure the journal, transfer the measurement to the dial bore gauge, and check the rod. They all came in between 22 and 24 10,000ths. Excellent! Accuracy of the ring gap is important, and it depends on what the engine is used for. As an engine builder, you determine what ring gap fits your needs. Since this is a high-performance engine that will definitely see some abuse, the ring gaps are opened up to 24 thousandths on the top ring and 26 thousandths on the second ring. We always gap the second compression ring first. For one, the second ring is usually gapped a little bigger. Plus, this gives you the time to dial everything in perfectly for that ultra-critical top ring gap. After gapping 16 rings, you'll be glad it's over, but you'll be even happier that the job is done to your liking. The right tools, like this Summit Racing ring squaring tool, helps you be consistent and accurate. Putting piston assemblies together is not hard, but it can be a bit challenging to install the lock. Fortunately, these locks are a solid piece of round wire instead of a spiral lock, so they go in a bit easier. The pistons are a Holley Power Pack kit forged from 2618 alloy. They have a 1mm, 1mm, 2mm ring pack, 927 thousandths heavy-duty wrist pins, a 20cc effective dish volume, and they are phosphate coated with a Grafal anti-friction coating on the skirts. We are almost ready to start assembling our stroker Windsor, but before we do that, I'd like to stop and take a little bit of time to talk about something that's very important for engine operation, and that is piston ring tension. Why? Because the ring tension is a big player in friction in the engine, and the more friction we can reduce, still control oil and seal combustion, the more power our engine will make. And I have a few examples here from Summit Racing equipment that will explain everything. Because of improvements in the material quality and machining techniques, the ring pack has gotten smaller and smaller over the years and still done a great job in sealing things up. Back in the day, a common size ring pack was a 5/64 top and second ring with a 3/16 oil ring. Now the oil ring was the main contributor to tension. A normal oil ring has about 20 to 25 pounds of tension when you pull it on a scale. An improvement to that size was to reduce the top and second compression rings to a 1/16 width. That helped with some of the friction, but it still had that 3/16 ring pack. You can reduce the pull on that ring pack by getting a lower tension oil ring. They're used in racing, but a better way of doing it is reduce the total size of all of the ring pack. Our piston has a 1mm, 1mm, 2mm ring pack, which not only reduces the friction, it also improves sealing because of the quality of the components. This stock ring setup pulls at about 22 pounds and is very notchy. Our vastly improved aftermarket setup pulls at about 10 pounds. Slick. It can be a little daunting picking what ring pack will work for your application, but if you contact the experts at Summit Racing's tech department, they can steer you in the right direction. Up next, our math teachers always said geometry was important, and they were right. With all clearances set and everything tuned in, we're ready for final assembly. The main bearings get a coat of high viscosity assembly lube. Windsor's have a one-piece rear main seal, and this one is Teflon based, so it goes on the crankshaft dry. It came with a plastic sleeve to make installation easier. The foundation for our stroker is a 4340 forged crankshaft from Eagle Specialty Products. It has a 4-inch stroke and a 125 thousandths radius on the journals for added strength. It was internally balanced at our favorite local machine shop, Shacklet Automotive Machine. The ARP main bolts are final torqued to 100 pound-feet. Thrust is set by wedging the crank forward and tightening the center main cap. Crankshaft end play measures at 3 thousandths. The hydraulic roller cam is made by Comp. Duration at 50 thousandths lift is 248 degrees on the intake and 258 degrees on the exhaust. Lobe separation angle is 114 degrees. Lift at the valve with our rocker arms is 646 thousandths on both the intake and exhaust. The camshaft thrust plate gets torqued down to 14 pound-feet. The camshaft dowel slides in, and the threaded oil gallery plugs are tightened down. Assembly lube goes on the plate, and then Comp's billet double roller timing set comes next. The camshaft is degreed and comes in at 106 degrees of intake centerline, which is 8 degrees advanced. Perfect for our street engine. While the degree wheel is still on, we'll mock up the cylinder head with checking springs in the number 1 position. We do this to check piston to valve clearance. The adjustable guide plates and 7/16 rocker studs are installed, along with the hydraulic roller lifters. Then an adjustable push rod is put into place to check valve train geometry and for push rod length. We'll mark the valve tip to help see where the rocker arm tip rides through its cycle. We're using Comp's 1.7 ratio Ultra Pro Magnum steel body rocker. Once it's set up, we'll use a steel plate to hold our magnetic base dial indicator. The valve train geometry is checked by opening the valve to half lift and looking at the relationship of the pivot point, rocker tip, and valve stem. This should create a 90-degree angle between the valve stem and the center line of the tip to fulcrum. The point where the valve is closest to the piston occurs within a range depending on the camshaft profile. Typically that is 8 to 14 degrees after TDC during split overlap on the intake, and the same range on the exhaust between 8 and 14 degrees before TDC on split overlap. We'll check within this range to find the closest clearance for both valves. Our minimum clearance on the intake side is 178 thousandths and 245 thousandths on the exhaust. Now we can check the amount of sweep on the top of the valve, which measures in at 65 thousandths. Outstanding! With the geometry looking great, we can measure the adjustable push rod to determine the correct push rod length. Ours will be 7-inch, 850 thousandths. Since we are not moving the cam, we'll apply some thread locker and torque the cam bolt to 45 pound-feet. This one has those like silky smooth rings.
Yep, the tiny, tiny low tension rings. Like pushing in with a pinky.
The piston and rod assemblies are installed in our squeaky clean bores. The connecting rods are Eagle Specialty Products H-beams with a 6/250 center to center length and a 9/28 bush small end for floating wrist pins. They are secured with ARP 2000 rod bolts. Final torque to achieve our proper bolt stretch is 90 pound-feet.
Sometimes people can get upset with our unconventional paint choices, but given this engine's Ford blue finish, the only thing getting triggered today is the ignition system. A great engine deserves a great paint job. After prepping the Windsor block with lacquer thinner, we'll mask off the bores, the valley, and the area around the timing cover, as well as any open ports. For a quality paint job, we're using this engine enamel that we got from Summit Racing Equipment. The color is Ford Blue. This paint can be brushed on, but for our application, we're going to thin it out a bit so we can use a spray gun. After prepping the block with primer, we'll do a light coat to ensure good coverage and finish it out with a few heavier coats to give it that rich, glossy look.
Next, we'll apply a thin bead of silicone on the block. After that, the timing cover gasket is gently laid into place. Finally, we'll add another thin bead of silicone for extra insurance. The timing cover is snugged down with ARP stainless steel fasteners and then tightened evenly. An ATI damper with a 10 o'clock timing pointer position is pressed on. Then our Holley EFI 36-1 crank trigger wheel is bolted on. For a modern EFI setup like we're using, this will give the ultimate in crankshaft position accuracy. It's torqued to 45 pound-feet. Our small block Ford crank trigger kit comes with a Hall effect pickup and bracket that bolts up to the timing cover. We also customized an MSD timing pointer so that we can precisely verify the #1 piston's position. We'll set true TDC on the #1 cylinder using a piston stop, then adjust the pointer accordingly. Next, we can turn the engine up to TDC on #1 cylinder, align the crankshaft sensor with the marked tooth, and set the air gap between the two at 40 thousandths. We have a bunch of great parts going on our stroker Windsor, but they don't mean a whole lot if you can't hold them together. And for that, we always go with a quality fastener from ARP. We are going to be bolting our cylinder heads on momentarily, so we ordered up one of their head bolt kits. These have an 8740 chrome moly fastener that has 180,000 psi of tensile strength. Now, these are not an OEM fastener, so they don't take an OEM spec. The great thing about ARP is they include with their kits parallel ground washers, their ARP Ultra Torque assembly lube, and most importantly, a detailed set of instructions. Because these aren't an OEM fastener, they don't take an OEM torque spec, so you can't just look one up online and just find a torque spec for an OEM application. The instructions tell you exactly how to torque the head so you get the maximum benefit. Because our Ford only has 10 head bolts per side, we need that maximum clamp load to seal the cylinder pressures we're going to make. So we're going to lube them up, stick them in.
ARP Ultra Torque assembly lube goes under the head of the bolt. Next, the washers slide on and the threads receive Ultra Torque as well. Our ARP head bolts are going to be holding on a set of AFR Renegade 220 cylinder heads that we got from Summit Racing Equipment. These are going to work great on our 410 stroker because they have a 220cc competition CNC ported intake port that flows up to 331 CFM. It all goes through a 2100 intake valve into a 58cc CNC combustion chamber and goes out through a 1570 exhaust valve. Both valves have 8mm stems, and for valve train control, we have a 1550 OD dual spring that's going to have 155 pounds on the seat and 475 pounds at open. We're going to put the rocker studs and guide plates on once we get our push rods, but for now, we'll get the cylinder heads bolted on and seal up our cylinders. The head gaskets are Cometic MLS with a 4100 bore and a 40 thousandths compressed thickness, which gives us a measured compression ratio of 10.36 to 1. User-friendly for pump gas. The heads are torqued in 3 steps to a value of 100 pound-feet. The Matco digital half-inch torque wrenches make it so convenient because we can pre-program all 3 torque values and switch between them at the push of a button.
All right.
Finally starting to actually look like an engine. It's the best part, right?
We even painted it a conventional Ford color.
Yeah, and we have a good solid bottom end, forged rotating assembly, nice, beautiful cylinder heads. I mean, this is going to be a nice engine when it's done, and it already looks nice.
Well, more importantly than looking nice is running nice, and I think it's going to run spectacular. I'm very excited about that.
Me too. For more information or to see more cool stuff like this, check out our website.
You're watching PowerNation.
With a high ram intake manifold, a coil-near-plug ignition system, and a Ford blue paint job, this engine has the style it takes to turn some heads.
And the guts it needs to make big power in the dyno cell.
Welcome to Engine Power. Today is a great day because we are going to be wrapping up our 410 cubic inch stroked Windsor that you can enter to win. This engine has a ton of great parts and a lot of hard work put into it. But before we go any further, we want to make sure you're caught up, and you know what that means.
Flashback.
After thoroughly prepping and cleaning the block, we check the clearances. Since this is a high-performance engine, ring gap was opened up to 24 thousandths on the top ring and 26 thousandths on the second ring. Then, we installed an Eagle 4340 forged crankshaft with a 4-inch stroke, followed by a Comp hydraulic roller cam.
Molle 2618 forged pistons and Eagle H-beam rods completed the rotating assembly. We sprayed Ford blue engine enamel on the block, and for the ultimate in accuracy, we installed a Holley EFI crank trigger system. Finally, we torqued down a set of AFR 220cc CNC ported cylinder heads with a 58cc combustion chamber.
The first thing we're going to tackle on our 410 Windsor is sealing up the oiling system, and that means getting our high volume oil pump, our pickup, and our pan installed. And to do that, we're going to use ARP fasteners. ARP makes a bunch of specific fastener kits for different engines, parts, and in a variety of finishes for your specific application. For our engine, we're going to be using their 6-point oil pump bolt kit, opting for their oil pickup stud kit, and using the nut that came with our main bolt kit to fasten the pickup to the mains. When we go to put the pan on, we'll be using one of their 12-point stainless oil pan stud kits. Not only are these going to look great, but it's also going to make it that much easier to put the oil pan on. With such a wide variety of kits, it's pretty easy to find quality fasteners for your engine from top to bottom. We're also going to be using an ARP chromoly oil pump drive shaft. It's a considerable upgrade from the OEM hex drive shaft that this engine would have come with. Since this will most likely be a street engine, we opted for a Melling high-volume oil pump from Summit Racing. It's torqued to 45 pound-feet. The pickup we're using comes with the Wyand oil pan kit and is matched to the shape and depth of the pan. To keep them securely in place, thread locker goes on one end of the studs and they're screwed into the block. We prefer studs instead of bolts for this application. They make it much easier to properly locate the gasket and pan.
We'll verify the distance between the pickup and the bottom of the pan using our Goodson straight edge. We've got 250 thousandths clearance, which is right in spec. Black RTV is sparingly added to the parting lines and in the corners before installing the gasket that comes with the oil pan kit. Before everything gets sealed up, we'll spray some valve train lube on the timing set. The Y pan has a 7-quart capacity and is made for swapping a 351 Windsor into a 79 through 93 Mustang. The studs receive ARP Ultra Torque and are tightened down to the compression stops of the gasket. The lifter bores and the lifters themselves receive break-in oil. These are Comp Cam's short travel extreme duty retrofit hydraulic rollers that have been REM polished.
In order to align them, we'll temporarily install the guide plates and rocker studs that came with our AFR heads. We'll also mock up the push rods and rockers, centering the rocker tips on the valve stems. After tightening the rocker studs, the rockers and push rods are removed so the guide plates can be tacked together. Finally, the rocker studs are removed one at a time, receive some thread sealer, and are torqued to 55 pound-feet.
After cleaning up our Comp 7/850 long push rods, we'll apply extreme pressure lube and slide them into place. It's also applied to the other end, the rocker stud threads, and the valve stem tips. The rockers are Comp Ultra Pro Magnum XDs with a 1.7 ratio and a full roller body. They're installed on TDC compression of each cylinder in the firing order. Preload is set to 1/8 turn past 0 lash. The polylocks are then torqued to 20 pound-feet.
How do you spell EFI?
Holley.
Now that we got our valve train installed, the next step is going to be putting on the intake manifold. And for that, we thought it'd be a great time to talk about the EFI selection we're going to use on this engine. It all starts with this Holley high ram small block Ford intake manifold and one of their 105mm throttle body tops. We painted this one matte black and we've color matched our fuel rails to give it a little extra pizzazz. It's all going to be filled out with a Scott Drake billet aluminum water neck, a set of 48 pound/hour Holley injectors, Holley EFI's 105mm throttle body with low RPM taper, and Holley EFI sensors throughout. To pair with our 36-1 crank trigger that's already on our engine, instead of a distributor, we're going to go with an MSD cam sync along with the ignition adapter harness for our unit. This is going to allow us to run one of the coolest systems on this engine, the Coil-Near-Plug ignition. For that, we're going to be using Holley EFI's Smart Coil Conversion Kit along with their LS Coil relocation brackets that we've prepped because we're going to weld them directly to the top of these Mr. Gasket polished cast aluminum valve covers, and then when we're done, we'll paint them our conventional color, Ford Blue. These not only look awesome, but they give us individual cylinder ignition control and allow the coils to have a longer saturation time before firing. It's all going to be controlled with a Holley Terminator X-Max ECU. These units are extremely easy to use, and they even come with a 3.5-inch touchscreen to do all the setup and tuning, or if you want to get a little bit deeper in the tune-up, you can use Holley's free laptop software. They come with 4 programmable inputs and 4 programmable outputs, and even a 1-bar internal map sensor for NA applications. You can switch it to an external map sensor, and the unit has integrated boost and nitrous control for your power adder of choice. There's a lot of great parts on this table, but we got to get them installed one by one, and we'll be that much closer to dynoing this bad boy. Up next, we break out the welder and the paint gun to give the Windsor some custom touches.
Then, it's dyno time. We're using an ARP 8740 intake stud kit for the Windsor. This makes it much easier to align the gaskets and the intake manifold during installation. These Fel-Pro gaskets are recommended by AFR. We applied some weather strip adhesive to the back of them to keep them in place. We'll apply some black silicone where the block meets the head to prevent oil seepage and a thin bead around the water ports to help them seal up.
With a glorious bead along each china wall, the intake manifold drops on, and we'll check the intake port alignment. Once we're happy, we'll slowly and evenly tighten it down, rechecking as we go. The intake top is held on with 12-point ARP stainless steel bolts that are torqued to 110 pound-inches. We'll fill the injector bungs with Holley's 48 pound-per-hour EV1 style injectors. We'll seal up the intake tract with our LS style throttle body and bolt on the Scott Drake billet aluminum water neck.
Since we don't know what application this engine will go in, we're going to install a Frostbite electric water pump, which we will use in the dyno cell. Now comes the fun part, some good old-fashioned fabrication using slightly modified LS coil relocation brackets. We'll get it centered on the Mr. Gasket cast aluminum valve covers and mark the location before it's tacked in place. The valve covers are prepped with an abrasive disc, cleaned with lacquer thinner, and the brackets are tacked in multiple places. These aren't structural welds, so a few beads will suffice.
To prep them for paint, the welds get a quick scrub with a stainless steel brush, and the valve covers are hit with a red scuff pad. Then they're washed with warm soapy water, rinsed, and blown dry. The valve covers get the same treatment as the block. After primer, a light coat for good coverage, and a few heavy coats for a glossy finish.
We'll apply a generous coat of valve train lube, bolt down the valve covers, and install the breathers. The Holley Smart Coils are designed to run directly off the Terminator X system. No coil drivers are needed. These are ready to handle an intense amount of horsepower, so they're more than enough for our Windsor. After the spark plugs are in, we'll install adapter plates to use our dyno headers. These have a 1 7/8 to 2-inch stepped primary and a 3-inch collector.
For our custom setup, we're going to build some custom wires out of this Holley EFI universal wire set. For a clean look, we'll build the spark plug wires to just the right length. Once they're marked, they are cut, stripped, and the terminal is crimped on. We'll grease the boot and the terminal so the boot slips on easily.
Up next, we do some wiring mods to make our coil-near-plug ignition run smooth as glass in the dyno cell.
Since we're talking so much about EFI, we thought it'd be a great time to talk about some of the more common sensors you'll see in an engine and how they work in today's tech tip. The first type measures rotational speed and position, and the one you're more commonly familiar with is probably a magnetic pulse generator or magnetic pickup sensor. This sensor has two wires, and when a magnetic trigger passes in front of it, it creates an alternating current signal. These are relatively simple because if the trigger is within range and the sensor is working, it will create an alternating current. The next type is a Hall effect sensor, which is a little bit more accurate than a magnetic pickup. This sensor still uses a magnetic trigger, but it has three wires, a 5-volt reference in, a ground, and a sensor wire that outputs a 5-volt digital DC signal that goes from 0 volts straight to 5 volts and back to 0. This makes it a lot more accurate and is generally used on EFI applications. If you're not measuring rotational speed but are measuring position, more than likely it's using a potentiometer. This sensor uses three wires, a 5-volt reference in, a ground, and a sensor signal wire that outputs an analog DC signal that goes between just above 0 and just below 5 volts as the resistance varies inside the sensor with rotation. A critical component of engine operation is measuring various pressures like oil and fuel pressure, and to do that, we're going to use a pressure transducer. These use three wires. They have a 5-volt reference in, a ground, and a sensor signal wire that outputs a DC analog signal between just above 0 and just below 5 volts as the resistance changes when pressure is applied. Just as important as pressures is temperatures, and for that we'll use a thermistor. There's two types, a positive type, which increases resistance as temperature increases, and negative type, which decreases resistance as temperature increases. The old style of thermistor generally had one wire going in that came directly from a gauge and used the engine as a ground. This means that the contact between the threads of the sensor and whatever it's going into are very important for sensor operation. A modern type has two wires, one that sends a signal to the ECU and one that operates as a sensor ground. This means that the sensor should operate as long as it is plugged in. These are just some of the common types of sensors, but there are a lot more you can run into in an engine. Hopefully this gives you a good indication of how they work, but if you need help finding a replacement for yours, you can talk to the experts at Summit Racing Equipment. We'll fill out our engine sensors with a throttle position sensor from Holley, along with their coolant temperature sensor. In order to run the Coil-Near-Plug setup, we have to modify the Terminator X main harness. First, the loom is removed. Then the new wires are added and taped to the existing harness. Each new wire is then cut, stripped, crimped, and put in the correct pin in the ECU connector. It seems a bit intimidating, but the included wiring diagram makes it simple. Finally, we can put the loom back on, tape everything up, and hook it up for good. Once the wiring is complete, we'll set up the dyno throttle linkage. Up next, with EFI this powerful, it's easy to get the Windsor dialed in to perfection. The last thing we need to do before we can start our engine is configure the ignition system in the Holley EFI software. The software makes it really easy. We just have to select our 36-1 crank trigger as the crank sensor and choose a single pulse input for our cam sync. We'll change the output to coil-on-plug and we're ready to go.
I feel like we're in like the space shuttle because there's like computers and
there's a lot of
displays
screens.
and which I like.
A lot of screens, but I'm excited.
I'm very excited.
This is just cool, I think, you know, putting a bunch of new technology on a little bit of an older engine,
right,
and just having the ability to do that, I think is really cool. So, see?
Wow.
No, that's nice. And the great thing about these systems is that, like, the idle and drivability stuff, the more it runs and the more it sees those conditions, the more it's going to learn. Once it gets up to temp, you know,
right,
it starts learning and it just gets better and better from there. So,
you know, the display on a Terminator X is still big. You can see everything.
Yeah, having that Pro Dash is really nice because then you can just have a gauge that comes right up. Yeah.
Let's see what 410 inches of Windsor sounds like with Coil-Near-Plug. What do they call it?
Coil-Near-Plug.
.463 pound-feet of torque, 434 horse. I am happy with the oil pressure. The fuel pressure looks good.
AFRs are right on target.
The AFRs are on target.
Yeah.
So let's make a full pull, turn the RPMs up a little bit.
Okay.
Clean right through the pull.
Sounding good.
All right, it's gonna need some tuning though. Okay, we'll take that. You know, it's 460 pound-feet of torque, 493 horse. It doesn't matter what engine it is. What's your first order of business on tuning?
Timing.
Timing. I agree with that.
So,
because timing has a huge effect on it, obviously, and that directly affects your airfield.
Airfields as well, so, yeah. So we start there.
You time for torque and you jet for horsepower. Well, we have electronical jets on this one. All right,
so we're at 30 degrees of timing now, so
that's going to be nowhere near enough.
Yeah, so you want to make a big jump here?
I would make a big swing at that one. I would put at least 4 or 5 degrees in it.
We'll just put 5 in it and make it 35. So let me do that. It's running great.
Yeah.
Looks great.
It's sexy. I really like it.
Can you say that on TV?
I just did. 476 pound-feet. That's a jump.
Yeah.
And 522 horse pressures.
Yeah, and I like how it smoothed out the graph
Yes.
too, you know, which we've seen every time. It just makes it a little bit smoother, so.
I'd put more time in
We'll
it.
put a little bit more in it. We'll go 2 degrees.
2
in it.
degrees of timing in it.
Okay.
Done?
Yep.
It's just that easy.
I mean, yeah, it's click, click, and bam.
Okay. So that's 481.7 pound-feet of torque, 526.8 horsepower.
Yeah.
Look at that. Look how nice that looks.
Yeah.
I like it when the graph is doing what it's supposed to. Okay.
Heck yeah.
If this was a carbahooter, now we'd start pulling jet, right?
Yeah.
Because O2-wise, there's no way in the pit of Hades this thing should run that rich on pump gas.
No.
So let's peel some fuel out of it. I would say let's set a target air fuel of 13.4-ish, 13.3, 13.4, somewhere in there.
Okay.
That's, I mean,
Yeah.
we're at 12.5. That's almost a full point.
That's a relatively large.
That's a
leap,
relatively large amount of fuel, but it has a relatively large amount of fuel going through it. If you're familiar with a combination, just because it's got fuel injection on it doesn't mean you're going to do anything inherently very much different.
Yeah, exactly.
All right.
And because we have a dyno, we can do this in a controlled manner. Like if
Absolutely.
you were doing this in a car that you're driving on the street, that's a little
I don't know if I
different.
do that.
That's a little different, yeah, but we can do this. So, all right. Hit it.
Let's let her rip and see what she does here. Oh baby, it's already going to be way better.
Oh, wow, yeah.
Woo, that was good.
Wow.
That was very, 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 very good. Woo.
Oh,
Look at that
big
stuff.
change, big jump.
562 horse, 504 pound-feet.
The crazy part is that
Whoa.
everywhere on the graph for torque, it makes 450 or over.
Yeah.
I mean, that's crazy. That's a great curve.
All right.
All right, let's pull the plug and go from there.
The ever so slight tan color of the porcelain indicates that our air fuel mix looks safe for our pump gas tune-up. Our choice of timing looks dead on for this power level. Well, by the way the tune-up looks on the screen, and by the way an old school guy looks at a plug for tune-up, I think we're going to leave this one right where it is.
Yeah, I mean, we don't normally do this a lot, putting some high-tech stuff like this on an old school workhorse, but using Holley EFI, the Coil-Near-Plug conversion, and the port fuel injection is really easy to do, and I agree, I think whatever this goes into, it's gonna be really nice.
New tech for an old school workhorse.
Like him.
What? If you want to see more cool tech and more cool builds, be sure to check out our website.